Well, first I'd like to thank the organizers for the invitation. It's always a great pleasure to be part of this conference. And today I'm going to talk about by Lipschitz and analytic radio equivalence between function germs on the complex plane. So the definition of strongly by Lipschitz equivalent germs is given below. So in some sense we say that F0 and F1 are strongly by Lipschitz equivalent if they can be embedded in a family Ft such that the following equation is satisfied for a family of vector fields Xt. Okay? Then this is the same if you consider a vector field X given below a germ of vector field at Cn, at the origin of Cn plus 1, then this is equivalent to say that x of f is 0, where f is defined with a third variable, as you see in this slide. Okay, so the definition of the associated cool vector field is given by the following equation, where the nabla here stands for the gradient and the other operators are very well known. So in 1969, Kuhl proved the following theorem, that any homogeneous polynomial ft of x and y, for any homogeneous polynomial like this, the associated Kuhl vector field is Lipschitz. So in particular, he shows that they are strongly by Lipschitz trivial, any family like that. So this gives the Lipschitz classification of such kind of objects. This classification is given in terms of the number of branches in the minofiber. So for the holomorphic equivalence, well, we have to recall the usual definition. So we say that F and G are holomorphically equivalent or analytically equivalent if there is a phi such that diffeomorphism, local diffeomorphism, satisfying the natural relations as below. So in 2018, I proved obtained the following result together with Bruno Scardo. That is, that the moduli space of germs of homogeneous function germs is given by M0n. This M stands for the Teichmüller space of any points, any unordered points in the Riemann sphere, and this is equivalent to the following quotient. So sim of P1 n, delta n is in fact defined below, so you pick for manifold M any copies of this object, and you get rid of the generalized diagonal, and then you let the symmetric group Sn act. Then the quotient is the space sim of P1 delta n. This is in fact considered to deal with roots of complex polynomials. So let me get an idea of where this comes from. In fact, the situation is that you have lines through the origin corresponding to the minofibers of this polynomial, and then when you blow up, they mark the Riemann sphere of the given by the exceptional divisor in any points. This n is the number of branches. So this is the reason why of this classification. So this is, well, in some sense, a good description, but the problem is if you want to understand the moduli number of this space, you have to work a little bit more. And excuse me. And the idea is the following: use the classical Lie group approach. You have a manifold M, you have a group G acting on this manifold M, and you pick a transversal section sigma as the one described in green. So then you shall consider a subgroup of G that preserves this transversal section. So that's the idea behind the simplifications that we're gonna see. Okay, so The first one is given by the following lemma. So we call that the automorphism of C star, C minus 0, excuse me, is given by this kind of diffeomorphisms. So the inversion and composed with a linear map, and then there is this equivalence. So you simplify the space, you look at a simpler group, and you can do it once and twice in order to obtain more simple space or coset describing the analytic moduli. So once again, so now we consider this manifold, hypersurface in fact, in the previous space, and then this is given by the sigma n of lambda equal to 1. This is the product of the any elements lambda 1 to lambda n. So this is in fact a kind of normal form for the polynomial. In some sense you can see this this way. So finally you obtain this relationship. So this hypersurface quotient to the action of by the action of the nth roots of unity and inversion. So since all the actions below are given by properly discontinuous groups, this tells us that the moduli number is n minus 1. So recall, Kuhl's theorem says that the Lipschitz type of reduced homogeneous function germs is given by the number of distinct branches of the minor fiber. As we saw, the analytic description is given by the quotient of the action of this group G by this space Wn. So, as we observed, there is moduli, and the moduli number is n minus 1. Okay, so that's enough for homogeneous families, homogeneous polynomials, but you have to keep in mind that this picture will appear once again in the quasi-homogeneous case. Let's take a look. So recall the definition of the quasi-homogeneous polynomials or function germs. In fact, they are given by those function germs that can be written in the following form in some holomorphic coordinates. So up to coordinate change, they are in fact quasi-homogeneous polynomials. So a polynomial like this can be split in the following form, where m and k are 0 or 1, because we are considering reduced quasi-homogeneous polynomials. This p and q are relatively prime, and so the other stuff is more or less obvious, because you have any branches for this. We used to call this the common part of the polynomial. This is Arnold's definition. So we have n plus m plus k distinct branches, and this is already an analytic invariant. So when you look to that object, we see at once that you can split the space in the following stratification below. The first case is already studied, because this is the homogeneous polynomials, where p and q are equal to 1. The second case, we shall call it the type 2 function germs. And as you see, most of the branches are smooth. All the branches are smooth, in fact. And some of them are tangent to the x-axis. And in the third case, they are in fact singular. So this will have an effect on the classification, of course. So let us take a closer look. So, okay, now let us recall the by Lipschitz invariants for this kind of objects. So he called it the classical definition of by Lipschitz equivalence, and he called that we have to calculate the polars in order to obtain some new invariants given by Henri and Parazinski. So we perform this calculation here. So due to the normal forms for these polynomials, we can split them and calculate the polars by taking the derivative with respect to y, for instance. And then in case p is greater to 1, you have the description, the first line of these equations. And in case p is equal to 1, we have the second line. So the p is equal to 1 is the type 2. P greater than 1 is the type 3. Okay? So I would like to call your attention for this relationship between the kappas and the lambdas, because the description of the analytic classification is given in terms of the kappas. Okay? So this sigma L's, they stand for the elementary symmetric polynomials. So due to these facts, we have the following parameterizations for these branches of the polar. Okay, so we have to keep this in mind, and sometimes we shall consider a fractionary approach for this parameterization, as in the Puiseux parameterization. Okay, so this is exactly what we're going to do now. Next, in fact, in 2003, Henri and Parazinski, they introduced some new by Lipschitz invariants in the following way. They consider the expansion of the restriction of f to its polars. So in the quasi-homogeneous case, we have explicit the polars in the slide before, and then when you do this calculation, this is a general case, okay? So when you do this calculation, when you expand f along this parameterization, you obtain the first term we're considering the fractionary expansion of gamma. And this h is rational due to this fact, and this is very well known, the way how we do that. And in the case of quasi-homogeneous polynomial, this h0 is automatically determined by the weights. So there is no new information in this case. So just this C0 will give us some new information about the Lipschitz type of this kind of germs. Okay, so as you see, in the quasi-homogeneous, in case p is greater than 1 or type 3, where we have this gamma 0 branch, the information given by that expansion is given this way. So in the other branches, the calculation is performed in this way. Okay, so we have this whole 0 in case p greater than 1, and whole L in every case. Okay, so the Lipschitz information is hidden in this whole L and whole 0. And so, the analytic information in this, is in lambdas. So you translate them to the kappas in order to understand the relationship between Lipschitz and analytic. That's the idea of the talk. Okay. So coming back to the analytic classification, in the same paper in 2018 with Cardua, we described also the other types, type 2 and 3, and the analytic description changed a little bit. So we don't have anymore the same spaces, but other spaces. And the reason why for the two cases below, well, this item 1 stands for the type 2, and the item 2 stands for the type 3. So a picture may enlighten a little bit the situation. So when you look to type 2, it's the first figure, and you apply a certain finite number of blowing ups, we obtain resolution like this. You are seeing the first figure. So in the last blow up, you have to fix the corner. So the symmetries of these objects are not allowed to interchange the origin, for instance, with infinity, as we could do in the homogeneous case, for instance. In the third, the description is a little bit more complicated because you have to fix the origin infinity So the groups change, the symmetries change, and the space changes because we can put a branch of the monofiber in any place, in the corner, for instance, because it's resolved. So with this picture in mind, we see that this makes sense. The first space and the second space, the quotients. And the symmetry group is M delta N is already defined, so we go ahead. So now in the type 2 case, what you have? N unordered points that correspond to the branches of the resolved singularity, and one point that corresponds to the ordered point that corresponds to the corner that you have to fix. And this 0 stands for the genus, the hemisphere. The notation comes from the study of type Miller spaces. It's classical in this scenario. So from the previous theorem, this gives the analytic classification of the type 2 singularities. But the point is that we want to understand the relationship between the analytic and Lipschitz singularities. So this is not so easy. Then let's take a look in how we did that. In a way very similar to the one I have described for the homogeneous case, we simplified the space, taking transversal sections and picking simpler groups. So this quotient group turns out to be isomorphic to this one, where this W0n minus 1 is a kind of normal form in which you ask the sum of the roots that appear in that splitting of homogeneous polynomials, in quasi-homogeneous polynomials, excuse me, as the sum is equal to 0. This is type 2. So the first reduction is this one, and then you obtain the linear group, okay, below. So in the second reduction, we pick this hypersurface inside the previous one, where now I ask not just the sum of them being equal to 1, but also the product being equal to 0, excuse me, but also the product being equal to 1. So then the description a little bit more simpler, because you have this variety and you are asking, or you are looking to the action of the nth roots of unity in this object. So this is a properly discontinuous group, and it's easier to understand what's going on. So this is once again a kind of normal form for the polynomials. Okay, so okay, and this map gives a kind of isomorphism between the lambdas and the kappas. So we'll translate the information from the lambdas to the kappas, and this will show very useful. Okay, so then we introduce some notation. First, that this HDPQ is in fact the quasi-homogeneous polynomials with a total quasi-homogeneous degree D, or weighted degree if you prefer, and P and Q are relatively prime, as we described before. And you want to call your attention to the fact that we just have to consider the case where the commute case, where K and M is equal to 0 because of the work of Fernandez and Huas. So the Lipschitz type is in fact determined by the commute part. Okay, so once we did all these correspondences, all these tasks, the following correspondence will tell us how to relate the Lipschitz and the analytic invariance in the type 2 case. So this relation will turn out to be, these relations will turn out to be given by the following system of equations. So the kappa now has all the information with the proper quotient space, the information that came from the lambdas, and then you have this map, epsilon from Cn minus 1 to Cn minus 1, taking the kappas into the holes. I call your attention how these kappas were defined. So the first result we have together with Cedinha is that this map determines the relationship between this invariance defined by Henri and Parushinsky and the analytic invariance. And in fact, this is a branched covering. So in the general case, in the generic case, we shall reach this upper bound n to the n minus 3. But when you have some, well, I don't have time to discuss the absence of genericity, but in fact, when the holes are 0, we don't reach this upper bound. Okay, so I guess I do not have much time to discuss the type 3 case in much detail, but it's more or less the same. Now we have to fix 2 points in the hemisphere. This is the reason why you have 2 and 2 in brackets, and this is simpler because now we look to C star delta n quotient by the linear group, and so you have to fix the origin infinity, so you don't have much homographies doing that. That's the idea. Once again, we ask we pick a normal form, asking lambda to be equal to 1, and then we look to this quotient, and this is equivalent to the original holomorphic space describing the holomorphic type of quasi-homogeneous polynomials of type 3. Okay, so the idea is very similar. So the difference is that we have to perform just one simplification, and then we obtain the following system of equations. And we have to take care because now we are in case p greater than 1, and then we have to consider that there is a quotient there. I didn't get much inside this. So then the space of Henri and Parushinsky invariants are given by this C, and as before, the pre-images by this new map epsilon will give all the information of the analytic types with the same Henri and Parushinsky invariants, and you obtain this result. So the difference now is that the upper bound changes, but it's more or less the similar thing. So some consequences I would like to discuss in the time I have. Well, the first fact is that summing up all this information when you look to quasi-homogeneous and non-homogeneous case, if you have a continuous family, this is a rigidity result. So if you fix the Henri-Parushinsky invariant, then they have to be analytically trivial. This family has to be analytically trivial. So this is the first consequence, and this is generalized result to Cedinha and Alexandre. And also, if you have a continuous family of holomorphic function germs, and if you ask this quasi-homogeneous parts to be in HDPQ, that is, we don't vary too much the topological type of these guys. That's the thing you are asking here. In fact, then and we fix the Henri-Parushinsky invariants, then the family will vary with fixed type, in fact. So the previous result will say that this P, this T, we must remove this T in the last line. You shall have a family, the original family equivalent to someone that the quasi-homogeneous part is fixed. That's the idea. So I don't believe I have time to discuss, but you may guess how the proof is given. And just to finish, I would like to call your attention to this result of Cedinha and Alexandre, that he asks here is for Rn, but anyway, he asks the quasi-homogeneous part to be fixed. So at least for the two-dimensional case, this is not a strong assumption. That's the fact. So, and in fact, to finish, well, what we saw here is that the Lipschitz analytic moduli in the quasi-homogeneous non-homogeneous case, there is no moduli, because this is given by branched coverings. So, but in the homogeneous case, there is moduli. So the reason seems to be that when you glue a branch like this, because if you look to the main divisor here, and you look to this P1 here, you see that this is the situation that happens in the homogeneous case. Also, the same happens here. So the point is that you glue these branches here, and in this case here and here, and this is the reason why you lost all this moduli, I guess. So this is something that has to be understood a little bit deeper, I think. So that's the idea of the talk. Thank you for your attention.